Hello and welcome to Chapter 4. Today we're going to start looking at the structure of an atom. So to begin with, what we're going to do is we're going to start talking about early ideas of matter so that we can see kind of how the process has evolved. So the first person we're going to talk about is Democritus, okay? He was the first person that proposed that matter was not infinitely divisible. He was the first person that said that matter was made up of tiny particles called atomos, which has been later translated over into the word atoms. And he said that atoms could not be created nor destroyed. So if you think about it, for the time frame that he was in, he actually had a pretty good basis for what we know today. However, there was a problem.
This is a study buddy.
Oh.
She snuggled right up in the blanket. She's out.
She'll be all bummed next week.
Yeah, when we come back. Yeah, this is our little pooch. Snuggled up back there.
I know, I see we got the email saying that we were going, we went to the volleyball game last night, and that's what everybody was asking, and I'm like, I haven't heard otherwise. I think they think that we're privy to, as of right now, it says we are, so.
Hallelujah.
Yep. Probably depends on how this week's game goes.
Maybe they'll only be here for 14 minutes.
I think it's funny though, because that's kind of, a lot of people make that comment, So.
So this wasn't.
But I really wonder if it wasn't with him being like genius. Because that's if they could prove that he was, or I know that they can prove it, but if the connection was made, and that ended there. And I get it. I mean, you don't want to end a season, but I just the fact that they wouldn't have done that for over here, or for your program, or robotics, or yes.
Yep.
So. But yeah, no, the game was good last night.
Good. Sounded like it was a tight match.
Yeah, well, the first game was good. It was like we had like kind of at least a comfort, but the second one I was like, oh, maybe this isn't gonna go.
A little discouraged. Like the girls were like, well, where are we gonna stay when we make it to states and stuff? And he's like, whoa. He goes, we need to go one match at a time. He said, I hate to throw this in your face, but what happened to the softball team last year? And then he was like, everybody kind of.
Yeah.
He said, they shouldn't have lost that game, or whatever.
Yeah, it's all momentum.
Uh-huh.
You gotta.
Yep. You just all you have to have is a team to beat you once, and you're done.
Yeah.
So doesn't have to be the best team. It just has to be a team that.
Yeah. I did feel a little bad though. Like about half the team never saw the court, and I guess I was talking to somebody. And they said that's kind of how he. And I get it. Like if it's a tight match and stuff, but like. It was making me nervous. Like that first game, I bet you half to 3/4 of the points that the other team scored were her mistakes in the back row. I'm like, she's not a back row player.
Yeah.
So I'm just going,
Well, and I don't know that they necessarily agree with the coaching. That she. What were we talking about in his appreciation? She goes, you need to go across the hall and have a chat. She goes, I don't know that the game plan was always the same, or that it changed when they brought some other kids up. And she goes, bringing kids up and letting them play over kids that have been working on the team and got us this far. She goes, that's not really sitting well with everybody. So, so I don't know.
Because they brought up young. Well, somebody was telling me though that they brought Miley Dalton and Leah Shoemaker up, and I didn't realize this. Well, their two setters are varsity players. So in my head, I'm going, you got two new people now that you got to train to. I don't know if I'd have done it during playoffs, but maybe do it. I don't know. I guess that's a hard.
Yeah.
But.
I'm glad I'm not I'm glad I'm not a coach.
Yeah. I know he's got hard shoes, and I mean, clearly what he does. I mean, their program's been pretty successful.
Right. Well, and I think the more successful your program is, the more questioned your stuff is.
Yeah.
It seemed like that. That's kind of how Graham even talked about Bill's discussion with them about mental health and stuff. I knew he was a wreck when we were out there. I mean, I'd stand there on the sideline and have halftime or whatever, and it's like,
Oh, that was all during football? Oh.
yeah, some of it was. And he was chewing down
Oh.
at the time. I mean, and yeah, I was pregnant at that time, and then the few years that followed that, it's good for him to be able to step away and step in to help, but not to have that whole responsibility on him. So, yeah, who knows? I feel like I'm just stitched together at the seams here for the next 48 hours, and so I called Little Caesars last night. I was in Bad X anyway, so I'm glad that I did it while I was there. They're like, no, we can't accept payment over the phone. Such ridiculousness. And so I thought, well, I wonder if I could order it online. I just wanted to see the whites of somebody's eyes and make sure and not depend on having 26 pizzas ordered that weren't going to be done at 5:45. And he's like, yeah, I got them down for the Bad X band. I said, it's not the Bad X band, it's the ugly band. So, I mean, what would the chances of being that Bad X band would be serving pizza at the same time? But, so Tammy Messing, Wade's mom, is going to pick them up.
Oh, okay.
For us.
Because I was going to say Harbor Beach has a, if it was going to be too much for them.
Yes. Oh, yeah. No, they were fine. They're like, nope, we got it. Yeah. So just said to Tammy, text me when you leave with the pizza, so I kind of know how much time we have left for rehearsal, and hopefully they'll have them done at 5:45 when you need them. And I every time I went to call, it was like noon or 5 or 6 o'clock, and I'm like, I don't want to call at busy time and do that. So, yeah. But I'm ready for this week to be over. I'm ready for it to be Sunday. Ooh, it must have frosted even more as the sun came out.
Oh, is there frost out there now?
Yeah, the grass is all covered.
Yeah.
So, at Tom, he's like, we need a different roller. He goes, you cannot roll a property this size with a 3-foot roller. Yeah, that's true. My dad has a bigger roller than that for his lawn.
Yeah.
So, all right. I'm going to get back to work here.
All right, I see ya. Other criticisms came from another philosopher called Aristotle. Now, Aristotle is considered one of the most influential Greek philosophers. So if you can imagine, when he rejected the idea of the atom, okay, there was a lot of people that also rejected the idea of the atom because Aristotle had that much influence. He personally didn't believe that empty space existed for atoms to move through. Now, on the crazy side of things, Aristotle's theory was matter was made up of earth, wind, and fire, and that's what he had people convinced of. So although we know that Democritus was on the right track, it took almost 2,000 years before somebody could start to prove that Aristotle was not necessarily correct and Democritus was a little bit more correct. So then along comes another philosopher called John Dalton. Now what John Dalton did is he actually refined the ideas that Democritus had by taking measurements and making careful observations. So he took more of a scientific approach. And what he did is he came up with a Dalton's atomic theory. Now, in a nutshell, Dalton's atomic theory said that matter was made up of extremely small particles called atoms. Atoms are indivisible and indestructible. He said that atoms of given elements were identical in size, mass, and chemical properties. And atoms of specific elements are different than those of another element. And finally, he said in a chemical reaction, atoms are separated, combined, or rearranged. Now, Dalton's atomic theory actually helped explain the conservation of mass, okay? The separation, combination, and rearrangement of atoms. And if you recall, the conservation of mass said that mass could be is neither created nor destroyed during a chemical reaction. It's conserved. And Dalton's atomic theory was a huge advancement towards what we know today to be the current atomic model. However, not all of Dalton's atomic theory was correct. He was incorrect about the atoms being indivisible because they can in fact be divided into several subatomic particles. He was also wrong about the fact that atoms of a given element have identical properties, okay? So atoms of the same elements can have slightly different masses, and we'll talk about that later on. So when we look at the conservation of mass, okay, just to show you how Dalton's atomic theory explains this, notice we start out with, I have two hydrogen here, or a hydrogen molecule. I have another hydrogen molecule down here with two hydrogen atoms, and I have an oxygen molecule that has two oxygen atoms. When these undergo a chemical change, they're going to form two water molecules. But if you look, these particles here separated and recombined to form the water molecules. But at the end of the day, over on the left, or the reactant side, I have 2, 4 hydrogens. When I look at my product side, I have 2, 4. And if you notice my oxygen, I have 2 oxygen here, and I have 2 oxygen over on the product side. Therefore, this kind of helps reiterate how the conservation of mass really works. Now we're going to jump in and look at section 4.2, which is defining the atom. So the atom is one of the smallest particles of an element that retains the actual properties of the element. Okay, so if you look at a copper penny, they say a copper penny will hold 2.9 times 10 to the 22nd atoms. Okay, that's a lot of atoms to fit on such a tiny little surface. They actually have to use a special machine called a scanning tunneling microscope to see the atoms. And you can see what one of those machines looks like right here. This machine is also typically referred to as an STM. So through the development of the atom, okay, people kind of started to buy into the idea. However, they still had questions that arose. Okay, they wanted to know what was the composition of an atom? What does it look like? How big is it? What color is it? Like all these different things. So what scientists did is they tried to start making connections between matter and electric charge. And by doing so, they were able to use what we call a cathode ray tube. Now, the cathode ray tube is a vacuum pump that passes electricity through a glass tube, and I have a picture coming up here soon. And then when you apply a voltage, electricity will pass from the negative side, or the cathode, to the positive side, which is the anode. So here's a picture of the cathode ray tube. Notice you have your negatively charged cathode, you have your positively charged anode, and the electrons then are going to flow through this tube. So by the end of the 1800s, scientists were convinced that cathodes were a stream of charged particles. Okay, so with the cathode ray tube, they were able to prove that these were charged particles. Okay, and they were convinced that particles were negatively charged. Now, since they changed the metals on the electrodes and they varied the pressure inside of the cathode ray tube, when they did all that stuff, they noticed that this did not change their end results. Therefore, scientists were able to conclude that the negative particles were in all forms of matter. We do have a video that we'll watch, but we'll have to watch this in class. So the negatively charged particles that they were seeing later became known as the electron. Okay, so an electron is a negatively charged particle that's part of all matter. They know that it has a -1 charge, and just so you know, sometimes you'll see an electron written as kind of like e raised to like a negative exponent. And I know like when I'm writing my notes and stuff, or when I'm writing that down like on paper, I will almost always write it as like e to the negative, just because it's a little bit shorter. Now they were able to find the mass of an electron to be 9.1 times 10 to the -28 grams. Okay, now that's the equivalent of 1 over 1,840, which is the mass of a hydrogen atom. So this is a pretty small mass. Now, we know that we have an electron and we know that we have a negative charge. The problem became we know that matter is neutral. So if we know that we have this existence of an electron and we know that that's a charged particles, people wanted to know why were they not getting shocked when they touch things, okay? Because if you have a negative charge and the overall charge is negative, when you touch things, you're going to get that shock, okay? Kind of like when you rub your feet along a carpet, or you put a balloon and you rub it in your hair or something like that, okay? So we know that matter is neutral, and if we have a negative charge, that means there has to be something that's counteracting that negative charge. So a scientist called J.J. Thomson proposed a model that consisted of a spherically shaped atom composed of uniformly distributed positive charges with electrons throughout it, okay? And this is what has been known as the plum pudding model. Now, the plum pudding model, this is kind of what J.J. Thomson was talking about. You have this sphere, and there's a bunch of positive and negatively charged particles throughout this kind of like medium, okay, that are going to counteract the charges. So if I really did not know what plum pudding was, okay, for the longest time. So I did put a picture on it for you guys to have a visual of it. Notice how it's like this medium, and then you got all these like little particles that are kind of floating throughout it. That's kind of how the plum pudding model became known, is that the particles floating about it were the positive and negative charges. Now, just so you are aware, the idea of the plum pudding model did not last for long. In the early 1900s, we had a scientist named Ernest Rutherford, and what he did is he began to study how positively charged particles interacted with solid matter. Now, the particles that he was looking at were actually radioactive particles called alpha particles, and alpha particles have a positive charge. Now, he worked with a group of scientists to see how these alpha particles would deflect as they passed through a thin piece of gold foil. So he took a narrow beam of alpha particles and aimed it at a piece of gold foil. Around the outside, there's a zinc sulfide coated screen that is surrounded by the foil, and it produces a flash of light when it's struck by an alpha particle. And I'll show you a picture of this here in just a second. So if you look at this, you have your radioactive source here that's shooting the alpha particles at this piece of gold foil in the middle. Then around the outer edges, we have that zinc sulfide screen. So what would happen is the particles would go, some of them go straight through, and then some of them were being deflected, and then some of them were kind of going off in opposite directions. So by noting where the flashes occurred, the scientists could determine if the atoms in the gold foil were deflecting the alpha particles or not. So based on this experiment that later became known as Rutherford's experiment, Rutherford was able to conclude that the plum pudding model was incorrect. Okay, it could not explain the results of his gold foil experiment. So based on the fact that Rutherford knew that alpha particles were positive, he knew that there were electrons that were present in all matter, and when he looked at the deflections based off his experiment, what he concluded is that atoms consisted mostly of empty space, and that this is where the electrons were able to move. He also found, or kind of figured, that most of the atom's positive charge and almost all of the mass was in the tiny dense region at the center of the atom, and he later called this the nucleus. And Rutherford was now able to explain that question as to how an atom was held together. He figured that the negatively charged electrons were held to the atom by the attraction to the positively charged nucleus. So by the 1920s, Rutherford was able to refine the nucleus concept. He concluded that the nucleus contained positively charged particles, which are called protons, and he knew that the protons carried a charge of +1. Okay, and one of Rutherford's co-workers, a guy named James Chadwick, who we'll hear about later on too, he discovered that the nucleus also contained a neutral particle called a neutron. So what he knew is that the mass of the neutron was close to that of the mass of the proton, but it does not carry an electric charge. Therefore, it's neutral. So to summarize everything in 4.2, what we know is we know that an electron, okay, has a symbol of E raised to the negative. Okay, it's surrounded in the space that goes around the nucleus. It has a negative charge, and the relative mass is 1 over 1,840, and the actual mass in grams is 9.11 times 10 to the negative 28. A proton is usually represented by a lowercase p. It's found in the nucleus. It has a +1 charge. The relative mass is about 1. And the actual mass you can see is 1.63 or 673 times 10 to the negative 24th. So you can tell that that is heavier than the mass of an electron. And then a neutron is represented with a lowercase n, can also be found in the nucleus. It does not have any charge, and the mass is very similar to that of the proton. So this is where we're going to stop for today. I hope you guys have a great day, and I will see you guys in class next week.